Hello everyone. If you are looking at this video, it means I have not went over question 3 in discussion. Question 3 is a difficult question. It used to be a homework question, but now it's a discussion question. And I doubt we can go over the entirety of it. So here's a walkthrough video of it. Before you watch this video, you should make sure you have all the knowledge we have mentioned in this section. Also, this recording is recorded at a Friday night, so if there are background noises, just ignore the background noises. So let's get started with question 3. Let's read the prompt a little as well, which is not going to be shown on the screen, so you'll have to open up the prompt on your own. One model that is even simpler than the linear model, which is a simple linear regression we have been talking about, is the constant model. Now, the constant model has its name because all the predictions we have to a specific response variable is just one constant. So this y hat here stands for our guess or our prediction of y. Every time we're going to predict a y, it's going to be equal to theta naught. So we keep giving this constant prediction. Now, why does that make sense? Well, sometimes it makes sense when the variable we're trying to predict is actually supposed to be constant. So for example, the amount of precipitation per year is supposed to be constant before we took care of global warming or some climate issue. Now, we also mentioned in our section that every model should be equipped with a loss function. The loss function that we discuss here for now is mean squared error. So, the mean square error of a constant function is equal to the average of all of the squares of the difference between the actual value and our constant prediction. Let me analyze this equation again. The 1 over n here stands for averaging, because we're averaging over n predictions, which are n predictions that we have to make. Yi here stands for the ith true value, which is the ith y that we're supposed to deal with. And last but not least, theta naught once again is our constant prediction, which I'm going to run on the board now. So how do we get this? We have to start with the original loss that we started with by using mean square error, and that is called the L2 loss. We also mentioned this in this section. The L2 loss takes an actual value and a predicted value. It has a hat, so it's the predicted value. And this is equal to the square of y, which is the actual value, minus once again the predicted value, and then squared. So the mean square error is actually just the average of all the L2 errors across all the predictions that we have to make. Now, having figured out the context of the problem, let's look at subpart A. If we use L2 loss, which we have written here, show that the best fitting estimate is the sample mean, such that the best theta naught we can get here is actually the average of y. So this brings us back to another question we had during our section, which is how exactly do we find the optimal parameter to minimize the loss? Well, let's try to formulate the question first. Every time we do a math problem, we're going to formulate it first. This is essentially how math works in upper division as well. So we know that the function we are supposed to minimize is the mean squared error. So we're going to try to find a theta naught that minimizes MSE of theta naught. And this means we're going to find the minimum of 1 over n times, once again, the summation term with respect to theta naught, which means the only thing we can adjust here is theta naught. Now, minimizing a squared function like this does look familiar. Maybe you have processed this information sometime 1 or 2 or 3 years ago, but this is actually easily doable using calculus. Remember that in calculus, we optimize a function, or we find the minimum or maximum of a function using derivatives. Or more specifically, we do it by finding critical points and what we then do is to use the second derivative test to search whether this critical point is a minimum or a maximum or not. Hopefully that brings back some memories. In the lecture, we mentioned this extra knowledge, which I did not go through discussion, and that is called convex functions. What are convex functions? Well, convex functions, if you think of it in a very informal way, there's another class about convex function, which I highly recommend later. Convex functions are essentially functions with convex curves, or completely convex curves. And the way you can prove that something is convex, there are essentially two ways that are currently available based on our knowledge. The first is you test whether the second derivative is always positive. And the second is you prove that the function is constant using an inequality called Jensen's inequality. The Jensen's inequality you will use during the assignment, so I'll not mention too much. If you have questions, you can reference the lecture or office hours. If I feel like I need to make another video on Jensen's inequality, which I don't think there's going to be the need to, but if I do think, then I'll make another video about this. One good thing is that the mean square error is a convex function. We'll go over this later. Oops, my selector did not work. Let's try it again. Okay, so then we can focus on trying to find the first order and the second order derivative of the MSE function with respect to theta naught, where we pay attention that we have to find both because we find the first derivative for the critical point and second derivative for testing whether the function is convex or not, and then we can conclude whether our critical point is a maximum or a minimum. So here's the tricky part. Unlike in one-dimensional calculus, which is brought over in Math 1A and most of Math 1B, we're currently dealing with something called multivariable calculus, which we also have a course for this, or maybe two. In multivariable calculus, we're interested in functions with multiple variables, and we want to take the derivative of a function with respect to a specific variable. Then we use this partial derivative. Partial derivative means we take the derivative of a function only based on one variable, and we keep every other variable constant. We should also pay attention to the fact that derivatives can be added together. What I specifically mean is that the derivative of 1 over n times the summation is actually equal to 1 over n times the sum of the derivatives with respect to theta naught of yi minus theta naught squared. This is probably already brought over in Math 1A or some preliminary stage of Math 53. So let's continue the derivation and only care about what's inside the summation. Inside the summation, we're expected to take the derivative of yi minus theta naught squared with respect to theta naught. And what we can do here is either we FOIL out the entire polynomial, or I simply use chain rule. If I use chain rule, then I'll get that the derivative is equal to -2 times yi minus theta naught. The negative, once again, comes from the chain rule. Okay, so I actually get that. This is also equivalent to the expression that I write here. Furthermore, pay attention that we can actually separate the summation. Well, since the negative of the theta naught and 2 over n cancels out each other, I'm just going to write it like this. Whenever we try to find a critical point, we also want to make sure the first derivative is 0. So let's massage this expression a little bit more, and we'll find that the sum of I equals 1 to n of theta naught is equal to the sum of from I equals 1 to n yi, and therefore theta naught times n is equal to the sum of all actual values, and therefore theta naught is equal to the average, which is 1 over n times the sum of all actual values. So we find one critical point. Now we must test whether this critical point is actually a maximum. And the way we can deal with it is to take the second order derivative of our loss function with respect to the entire cost function. Oh, sorry, with respect to theta naught. I was at a loss of words. And this we can actually just do by taking the derivative of its first order derivative, which we have computed already, the first order derivative is equal to negative 2 over n times sum of I of yi minus theta naught. If we take this derivative by putting the derivative into the sum, which makes everything easier to look at, then we get that the derivative within the summation is actually equal to negative 1 because we're taking it with respect to theta naught. So this is equal to negative 1. So I sum negative 1 by n times, and then I multiply it by negative 2 over n. What this means is that the second order derivative is actually equal to 2, and this is always larger than 0. So what this tells about our loss function is that the loss function is convex. And not only that, we also learned that the critical point we find is a maximum. Oh, sorry, is a minimum. Remember that when the second order is positive, the function's curve opens upwards, and therefore when it has a critical point, it will be at the lowest point of the curve, or else it's impossible for the curve to open upwards. So therefore, the optimal theta naught, which we express as theta naught hat, is equal to the average of all the actual values. Okay, so now we have solved problem A, and the general thinking process is just to try to minimize the loss and find the theta naught that can minimize the loss. The way we did that was to try to use calculus to find the minimum the theta naught that causes the minimum function value. And to use calculus for this, we will calculate the first order derivative and the second order derivative. Let's get some breathe time, and let's move on to question B. In question B, now we have a weirder loss, which is called the L1 loss. The L1 loss also takes in an actual value and the predicted value, and it's equal to the absolute value of the actual minus the predicted. So once you see it's always positive, once again you see that the loss is always positive because having a negative loss is a little difficult to try to interpret. Now we must find the best fitting estimate using L1 loss, which means we want to minimize with respect to theta naught the average of L1 loss. And that is equal to trying to minimize the average of the absolute value of yi minus theta naught. This is a little bit tricky to do a derivative with, but we can still try. Let's look at the function of the absolute value. When I plot the function f of x is equal to absolute x, then I see a V-shaped curve like this, where when the derivative works like a piecewise function, where derivative is 1 when x is equal to, x is larger than 0, and negative 1 when x is smaller than 0. When x is equal to 0, we would say that the derivative is not defined, and the reason you can check Math 1a for it, perhaps. Now, let's look at how this derivative plays with a constant shift. Suppose now, instead, I use a function f of x is equal to square root of x minus 1, then the V-shaped curve will be 0 at x equals 1 instead, and my piecewise function changes a little bit. df dx is now equal to 1 when x is larger than 1, and then vice versa. So from this we can vaguely observe that suppose f of x is equal to the absolute value of x minus a, which a is a scalar, then the derivative can be phrased as 1 when x is larger than a, negative 1 when x is less than a. Okay, so now knowing that, let's try to take the derivative of the mean absolute error, which is the average of all L1, with respect to theta naught. And inside that's absolute value of yi minus theta naught. So if we take the derivative of this, which we can do by once again moving the derivative inside the summation, we will notice that we're actually just calculating 1 over n times the number of points, or the number of yi's that are larger than theta naught minus the number of yi's that are smaller than theta naught. This actually poses an interesting question. The question also says that we can assume n is not, so the median is well defined, so there's only one median, and we also have, so then it's also possible to have an even number of yi that's larger than theta naught while having an even number of yi that is smaller than theta naught. We notice that this value is equal to 0 when the number of yi's that are larger than theta naught is equal to the number of yi's that are smaller than theta naught. So therefore, theta naught has to be a value such that half of yi's is larger than it, and another half of yi's are smaller than it. Therefore, we have to dictate that the theta naught is actually the middle number of all of the yi's, and that means theta naught is equal to median of yi. And this is the only way to minimize the loss function. At this point, the loss function is going to be 1 over n times the absolute value of yi minus theta naught, which is a sum of convex functions. So that means that the MAE itself is also convex. How do we see that the absolute value of yi minus theta naught is convex? Well, we can look at its curve, and we see that the curve is actually convex. To prove that it's convex, you can either continue to use the second derivative test, which is a little bit harder to use, or you can use the Jensen's inequality, which is most likely going to help you, because the second derivative is sometimes undefined on the curve. Okay. So if we use Jensen's inequality, we'll also notice something weird, which is that the Jensen's inequality works more like a Jensen's inequality, because if I pick 2 points on the absolute value curve, then I see that this line segment between the line segment between 2 points on the curve doesn't really go above my function curve, but actually it's equal to the function curve. So in this case, we can call this section of the function either convex or concave, because the Jensen's inequality works in the equality case. There is something called strict convexity, if you're interested in, that focuses on how to distinguish this phenomenon with other convex function. But for now, we'll say that f of x is a convex function, because when we take other 2 points that are on the different side of the scalar that we're trying to subtract from, the curve does go above the function curve. The line segment goes above the function curve. Okay, so that's a very informal explanation of why the absolute value function is convex, and the more rigorous proof you have to do via Jensen's inequality. And also, the solution mentions an interesting property, which is that the sum of convex functions is convex. Let me address a little more on this, because this is actually a proof that will not take too much time. So suppose we have a function f of x that is equal to f1x plus f2x plus plus f of n fn of x, where for all I between 1 to n as an integer, f of I is convex in x. Then, if I take the second derivative of all of these functions, then that's equal to summing over the second derivative of all the subfunctions of f. But we also know that this must be larger than 0, because all the partial derivatives of the convex function must be larger or equal to 0. So then we have that the sum of convex functions must also be convex. Once again, it's an interesting point that even if the second order derivative is 0, you can call it a convex function. For example, a line can also be called a convex function. But I'm not going to address, once again, I'm not going to address this too much because it might confuse a lot of people, and this is out of scope. Just keep in mind that a line can sometimes be a convex function. In that case, it's also not too bad to prove that the absolute value is a convex function using some derivative tricks. All right, that's enough digression for out of scope content. Now let's come back to the question and talk about part C. In part C, it says that we can often check how sensitive a model is based on estimating equation. We'll talk a little more about model sensitivity towards the end of this video because it's a little bit of a complex topic. That is, how will the estimator theta naught change when an outlier is introduced? So let's think, part C wants us to use L2 loss first. And remember that when we're using L2, theta naught is equal to the average of all yi's. What do you think will happen to theta naught if we take a single yi value and make it larger and larger while holding all the other values from x and y fixed? So if I give a graphic demonstration, what this means is I'm going to have a lot of points which look like they have a general pattern, but I'm going to make one specific point higher, and then as you can see, the regression line might change a bit to account for this value, but how much would it try to account for? Well, let's think about this. Suppose I have a specific yi that I keep rising above for. Given that theta naught is the mean of all yi, then the more I rise this yi, the more that I rise this specific point, which let's call yj for clarity, the more I rise yj, the more the average of theta naught would increase, right? So for example, let's say that theta naught is maybe equal to something like 1 over n times sum of a lot of yi. And then I also suddenly add another specific value, yj prime minus yj, which stands for the amount after which I change yj. Then we can see that this value is actually unbounded. I can just make yj prime as high as possible, and then theta naught would then have to change the corresponding amount as much as possible. Even more cruelly, I can make yj prime just be equal to a multiple of n, and that will lead theta naught to increase in the scale of natural integers, and then eventually I can just make yj prime a very large number to make theta naught very, very high. So therefore, the answer to this question is actually option 3. Theta naught can change unboundedly when I maliciously change yj to a high number. Now, what does this mean? Let's talk about the context of this and having outlier data. We have learned before that an outlier data stands for a specific data point that is very different from the crowd of the other data that we observe, and more often than not, these outliers are going to be either having extremely high values or extremely low values. And what that means is that if we use L2 loss, then these extremely high values or extremely low values will come in turn to affect the average term and therefore introduce more deviation to the estimator that we're using. And therefore, our model is not really robust to noise or robust to outliers when the outlier influences our model's prediction by too much, such that by accommodating for the outlier by increasing our mean, which is going to be our optimal theta naught, we actually lose all the other considerations we had for other data that is not the outlier. And therefore, this is why it's important for you to remove the outlier data before starting doing machine learning or modeling. But this can actually be addressed or at least mitigated by using a different loss. So let's look at part D to explain why I just said this. In part D, instead we use the L1 loss, where, keep in mind, that L0 is now equal to instead median of yi. So what does this change from mean to median really mean? Let's plot yi on a histogram, which is not going to look like a histogram because I'm not going to draw all the bars. And let's say that my original yi is here. Or the change that I'm going to introduce for yj is here. I can increase yj to a really large number. Let's say that original median is here, which I'm going to call ym. So originally my theta naught is going to be equal to ym for optimal because ym is the median. I can change my yj to be really large, and eventually it replaces the median and becomes the new median. Then theta naught hat now becomes yj instead, which is going to be slightly higher than the median. So j is now equal to basically, or at least on the order of, on the order from the smallest to the largest value, yj is currently at order of something like m plus 1 over 2. Okay, I am going to increase yj once again such that it is larger than the next value in the line. So the original median is now something like at the order of m minus 1 over 2. And I'm going to increase yj such that its current value is going to be, actually no, this is going to be m plus 1 over 2 minus 1 because it reduces order by 1. I'm going to increase the order of yj such that it's equal to m minus 1 over 2 plus 1. Then even if I increase yj, I now have this new median which is at the position of n over 1 over n plus 1 over 2 in terms of descending order. And my theta naught is now going to be stabilized, or not stabilized, it's going to be stuck with the value that was smaller than j, yj. And now, however much I increase yj, my median is stuck at this value that was just smaller than yj in the previous moment. And therefore, we can first detect that there is going to be change if I change yj. So option 1 is incorrect. Theta naught would somehow change. But there's also a limit to which theta naught hat would change as I change yj, so option 3 is also wrong. Therefore, the answer is actually option 2. And what does this tell us about the sensitivity of the model? Well, now I learned that even if I maliciously increase a data so high that it looks like an extreme outlier, my model's estimator is not going to change too much, and I can still account for all the other data that I'm trying to bother for around the median. So using mean absolute loss makes our model more robust to outliers, which means it performs better under outliers than the model I use when I use MSE. And therefore, the lesson to take away is that the loss function we choose for the model actually matters. And by choosing different loss, we change how our model behaves in terms of trying to accommodate for the different data points we have in our data set. Okay, so that's a full walkthrough of question 3, which once again used to be a very painstaking homework question. I don't know why it's in discussion, but it is meaningful to talk about this question in discussion. The takeaway I wish you take away from the video is the general problem-solving procedure we can use when we encounter math-related free response problems in Data 100. Similar questions might appear in exams, but it is more important that you apply this knowledge to something that you're working on in real life, because data science is not helpful without application. Alright, that's it. Don't look at the other videos in the channel, they're not meant for you.